Hi, this is Chuck Andrika of the National Free Flight Society Youth Development Program. This video is put together to give you an introduction to the flying events, both Wright stuff and electric Wright stuff, for the 2021-2022 school year in Science Olympiad. This video is intended for coach clinics across the country. And it's being developed for the New Mexico Coaches Clinic, which will be virtual. The statements and interpretations in this video are not to be taken as official, but there are current reading of the rules and intended to provide guidance to you as a coach or administrator in leading your students to competing in Wright stuff and electric Wright stuff. Always return to the rules and read them yourself to understand exactly what the rules are saying. And if you have questions on the rules, please submit an FAQ to Science Olympiad to get further official clarification on your question. In the presentation today, we'll look at the event descriptions and rules briefly. The airplanes in both classes are very similar, so we'll start by looking at the common areas of these airplanes, and then we'll look at the details of electric Wright stuff in B division, which is a new event, and then Wright stuff in the C division. We'll also touch on the sources of material and sources of aid as you progress through the school year. A little bit on building techniques, a couple of hints to help you out, and then a little bit on flying, how to get your successful first few flights in. So the common rules for the B and C division events and the flying events. First of all, it's a pre-build event. This is not a design event, but rather it is a build and then flight optimization event. So it's data driven. You want to fly as much as you possibly can. It's a powered indoor monoplane airplane, meaning it's not a biplane. It's got a single wing and a single stabilizer, and it's flown for duration in an indoor facility. You can use any materials to build the airplane except for boron. And you can also bring any tools into the test area that you want. The score will be the best of your two flights in duration. And then there are some bonuses that we'll discuss. Kits are permitted because it's not a design event, but they must be student built. Every part that's glued together must be done by the student. You can't have any pre-glued parts. You can't have any pre-covered parts. So as I mentioned, this is not a design event, but a flight optimization event. Data collection and recording is really critical to success. Your logbook is not just a requirement in the rules, it's key to success in this event. You need to build light and try and reach the minimum allowed weight in the class. It should be fairly easy to reach the minimum weight, especially if you're using one of the many available kits. Electric Wright stuff, you're carrying the weight of a motor and a capacitor, and you really have to pay attention to building lightly. Not only do you need to build light, but you need to build accurately. Crooked or twisted planes simply don't fly well. And again, taking lots of data means flying a lot. Getting time in the gym is going to be critical to your success. Some of the common parameters, first of all, you can build from a kit, you can build from published plans, you can build from student design plans, you can build from coach design plans. Any source for plans or kits is permissible. Classes both have a 45 centimeter wingspan. That's the length from one tip of the wing to the other tip of the wing, and a 9 centimeter cord. That's from the leading edge to the trailing edge. Now, those are the maximums allowed. You don't want to try and build right to those maximums. I'd suggest a millimeter less than 9 centimeters on the cord and a millimeter less than 45 centimeters on the span. These will be measured using gauges at your competition, and if you're oversized, you get tiered. The stabilizer or stab similarly has a span of 28 inches and a chord maximum of 28 centimeters and a chord of 7 centimeters. The propeller may be purchased. This is an ICARA propeller on this plane, or it can be built by the students. There are videos available from NIFIS on our resource site on how to build a propeller from scratch. This particular plane is not a Science Olympiad plane, but it's very similar in size to the plane we'll be flying this year. There is a 10% bonus for coloring with black marker one panel between two ribs from the leading edge to the trailing edge. So this entire panel would have to be colored. If you have tip plates, one tip plate can be colored. Has to be colored with black marker. That's the only thing that's allowed for coloring. Or it can be covered with black tissue. Your plane needs to be labeled for identification. Your school name would be suitable for the labeling. And up to 2 planes can be presented for inspection by the 2-student team. If there are any construction violations, dimensionally or material-wise, your planes will be non-compliant and they'll be tiered. What's not mentioned in the parameters is the plane configuration. This is what we would call a conventional configuration with a front wing, front propeller, rear stabilizer. A canard configuration would have the wing toward the back of the plane and the stabilizer at the front. A tractor has the propeller in the front, like this plane, whereas a pusher could have the propeller in the rear. The simplest construction and the design with the most information out there on the web is going to be your conventional plane with a tractor propeller. The length of the plane is not specified, and then the format of the wings is not specified. On the slide, we see a flat wing with tip plates. In this case, we see a wing with simple dihedral. You can also have a wing that's flat in the middle and then diagonal dihedral tips. So there's various ways to build the format of the wing. Okay, common to both events are some of the processes of flying. First of all, the flying will occur indoors, preferably in a room with the AC turned off or the air handling units, and the room dimensions are supposed to be published in advance. If you're not getting room dimensions from your state or region or invitational leaders, you want to quiz them at least a week in advance because you're going to want to tune your flying to the height of that gym. Once the students enter the competition area, there can be no coaching or communication with parents, with coaches, with other students. Only the participants may touch the plane. This is important. This means don't let the officials attempt to measure your plane for you. You make the measurements on the plane. That way, if it's broken, you're the only ones to blame. We don't want to have officials in the getting blamed for breaking an airplane. The flight log, we're going to talk more about it in a little bit, but if it's not present, it's a 30% penalty. It doesn't tear you, but it might as well. That's a big penalty. If it's incomplete, it's a 10% penalty. There's no grading of the log. It's either complete, incomplete, or missing. Once you've checked in, you can use some of your flying time to do trim flights, but you must announce them as trim. If you announce them as official, or if you fail to announce at all, then the flight will be considered official. Now, the event organizers have the option of allowing trim flights prior to your check-in as long as you give way to official flights. And then they don't allow trim flights in the last hour of the competition day, other than trim flights within your flying time. So let's look at that flying time, the clock. There's an 8-minute flying window that starts with your first flight after you've checked in, whether that flight is official or trim, whether it's powered or unpowered. So any flight that occurs after you've checked in and gotten the go-ahead from the officials will start this 8-minute window. Prior to the 8-minute window, you have a preparation period. This starts when the judges give you your checked-in rubber, or in the case of electric Wright stuff, your charger. At that point, your prep period starts. 3 minutes for Wright stuff, 2 minutes for electric Wright stuff. If you start your first flight in that prep period window, it ends the prep period and you get a 5% bonus on your score. You can even do just a quick test flight. If you're almost done setting up your plane for official flight, grab your second plane, get a quick test flight right at the end of 3 minutes, so you get this bonus. It's a fairly easy bonus to get, and it's intended to keep the process moving along. If you don't get a launch in the first 3 minutes for Wright stuff, 2 minutes for electric Wright stuff, that prep period ends and your 8-minute flying window starts, even though you didn't have a flight during that time. Once you've entered the event and been checked in, there's no time out in this prep period or the full 8-minute period for retrieval or repair. So it's important to have 2 planes. We've seen planes get hung up in the rafters, and it's a lot quicker to get your second plane out for your second flight than to try and recover and repair the plane that got stuck. If a flight starts in your 8-minute window, it can go to completion even if the 8-minute window ends. But if say your second flight has not started when the 8 minutes expire, you're done. You don't get to do your second flight. As mentioned before, your score is the best duration of the 2 official flights plus any bonuses, and construction violations are tiered. The flight log. These are critical to learning, to trimming, to improving. It's a data-driven event. It's highly empirical, and having the log allows you to go back and see what you've learned, what worked, what didn't, and make adjustments to the plane based on the log. There are both required and student-selected entries in the log, but generally we see far more entry columns in the log than the minimum requirement. It's also 10 flights minimum. We typically, before we get to nationals, we'll have 300 to 500 flights, all logged. So you want the 10 flights as a minimum to get a complete log, but you want a lot more flights than that logged. Any numeric values, this is new this year, must be in proper metric units. So if you've got some things like the log shown here has the altitude in feet, you'll want to convert that to metric units. You may have things that are measured with tools that only give English units. In that case, you're going to have to convert those in a separate column in the log, or rewrite your log after your flying session in proper metric units. The build log is a part of the flight log, and this is new this year. This has to include the materials used in the construction of the plane, and that can be on a plan as shown here, where the materials and the sizes and so forth are spelled out on the plan, or you can have a bill of materials. It doesn't specify how those have to be presented. However, you do have to have a labeled diagram identifying and describing the parts of the plane. I think a plan like this would probably qualify. It doesn't clearly say what that description has to entail or what has to be identified, so you can't go wrong with identifying every item on the plane and describing what it was made from. Appropriate metric units, again, must be included. And this year they're requiring a cover page with the team name and your number, which will differ at each event you go to. Now here's another part of the build log that is new this year. If you use any kind of computer controlled machine to make any part, it says used to build the device or any component thereof, there are additional log requirements. And a computer controlled machine includes a 3D printer, a CNC router, a laser cutter, or anything of that sort. So if those components or those tools were used to make any component of the plane, you have to give information about the tool, the software, and materials used. It doesn't specify what information, but I would certainly be given the make and model of the tool, the make of the software, and what the materials were used, say on a 3D printer that you use PLA. They want digital details of any digital files used. In other words, if you downloaded a CAD file, an STL file, an object file, or a G-code file for your 3D printer or for your laser cutter, and use that file, you need to indicate where it was obtained, including a web link if you downloaded it. If the students wrote the file, which is the ideal thing to do, then you need to detail that out, that the students did it in such and such a language, and so forth. And then a description of how the final device was constructed from the tool created components. So in other words, what steps did the students have to take given this printed or laser cut or routed part to incorporate that part into the final design. These are somewhat open-ended, but I would err toward more detail rather than less detail. As a caution, some kits include laser cut or 3D printed parts. You will probably benefit to talk to the kit makers and get this information for those parts just in case, because they are CNC machined parts that are being incorporated into the plane, even though they were part of a kit. If you have questions on this area, you need to submit an FAQ. Students also must be able to answer questions regarding the design, construction, and operation of the plane. This is an opportunity for the judges to dig in a little bit and to understand or verify that the students are the ones that built the plane and that they have learned through the process. So as an event supervisor in the past, here's some of the issues and observations I've made. One is logs are usually very insufficient. If they're complete, most logs I see, even at the state level, only have 10 entries. Some of them have too few columns, but at most I tend to see the bare minimum required number of columns. The logs are a critical element for improvement of your plane. You should log every flight and you should diligently keep those logs. You're not going to get marked down if you only have 10 entries in the minimum number of columns, but the log isn't doing its job. Crooked construction, we see a lot of that. The kits tend to have a lot of detail on how to build the plane straight, build it on a smooth building board. You can go down the Hobby Lobby and for a couple dollars get a 1/2 inch thick piece of foam board. This has a paper laminate on both sides of a 1/2 inch thick piece of foam and use pins to hold the plane parts down to that. Don't pin through the part, but put pins clamping the part down to the board. Untrimmed models. We're going to touch on trimming in just a bit, but the models that are untrimmed, I see some very well-built models that obviously have never been made to fly successfully. The instructions in most of the kits are very detailed on how to trim your model and get it flying. Heavy models is a big issue. You want to be as close to the minimum weight as you can get. Too much glue tends to be the primary reason for heavy models, and we'll touch on that in just a bit. Most planes are reasonably built, but not reasonably trimmed. You need to do a circle for any reasonable duration, and the circle will be a left-hand circle for the normal prop direction in the US. We'll talk a little about trimming, but basically you start with low power and work your way up to higher power, making adjustments as you go. And here's one final key that I've seen. I've seen some students practice in the morning in the gym. We're going to have a contest, but then they see another team do really well and they adjust their approach based on what they see the other team doing. So they come in and do something they didn't do in practice, and the plane dives into the ground or gets hung up in the girders. So practice what you're going to compete. How can you improve your game once you have a plane flying? This year's plane has great proportions. It should be a very stable platform. It should be a good starting point. It should be a lot of fun to fly. Bottom line is spend more time in the gym than you do in the build. Keep detailed logs. We've covered that several times. Read and know and follow your rules. Don't get tiered because you forgot to read the rules. There are very good online videos. The National Free Flight Society is putting together videos on our YouTube channel. J&H Aerospace has some great videos on trimming and other aspects, build videos as well. Use the resources that you'll find at the end of this presentation, especially the online forum at Scioli. This forum is a great place to discuss the problems you're having and look for solutions. Myself, Coach Brian, and Coach Jeff Anderson are regularly on the forum, and we'll usually get back to you within a day with thoughts about how to improve your situation. We may ask you for more information because a lot of times we hear, my plane's not flying good, what should I do? We need very specific information, where your CG is, the measurements of your incidents, and so forth, in order to help you out. Okay, so let's look at electric Wright stuff. The electric Wright stuff, additional parameters, the power pack is very specific this year. It's powered by a 5 farad, 3-volt supercapacitor. Those are maximum ratings, but you want to take it to the maximum on the farads. You could use a 3-volt or a 2.7-volt supercapacitor. They're roughly equivalent. I don't see a big difference there. This can be charged up to 3 volts from 2 alkaline cells up to D size. That's your charger. You can't have a plug-in charger. You can't charge it from LiPo batteries or anything like that. So basically 2 1.5 volt D size cells will make a battery at about 3 volts, and you can charge up to that level. It's a direct drive prop. The prop is directly pressed onto the front of the motor. There's no gearbox, but there's no specified prop size. You're going to find these are going to take pretty small props because the motors in this size range tend to be very high revving motors. The minimum mass of the airplane is 9.5 grams. That's all up with the motor on it, ready to fly. This is the same weight as the Wright stuff. The Wright stuff plain is 8 grams, but you're allowed 1.5 grams of rubber motor. So they're both 9.5 grams in the air. The capacitor on the plane and the battery in your charger must be able to be viewed by the judges. Now, the battery charger, the battery holder may have a removable cover. As long as you can show it to the judges and show them that you don't have a LiPo battery or something like that. They need to read the label on the battery and the label on the capacitor. So if you glue your capacitor on, make sure you glue it in such a way that you can still read the ratings on the capacitor. If you have a capacitor that doesn't have the outer wrapper on it, and so it doesn't have a rating printed on the capacitor, it's not a legal capacitor. The on-plane power system may consist of the propeller, the motor, the capacitor, a switch, wires, and connectors. That's all. Basically, they're not allowing any kind of speed controller or other kind of electronics. The charger may consist of batteries, a battery holder, wiring, connectors, and a resistor. Now, the rules do say that one of the required columns in the log sheet can either be your charge time or your charge voltage, what you charged up to. In other words, the voltage measured by at the end of charging. So that implies that you can have a voltmeter. It's not necessarily part of the charger, but in order to generate the data they're asking for, you would need a voltmeter. One thing that we found as we built our planes, wires weigh a lot. We had over 3 grams worth of wires on our plane. If you go to real fine wires, you could drop a lot of voltage between the capacitor and the motor. So there's a balance there. You want to experiment with various finer wires. You could even experiment without having insulation on the wires. As long as you can keep the wires separate by gluing them to the motor stick, there's no real need for the weight of insulation. The flight log requires either the charging duration in seconds or the capacitor voltage at launch. The flight time measured by a stopwatch, and the estimated or measured altitude. You can estimate altitude fairly easily by comparing to the basketball rim at the edge of the room. That's typically going to be at 10 feet, and knowing your room height. You can make some estimate of the altitude. Don't forget to convert that to metric if you're used to thinking in feet. At least 3 additional columns are required, some of them that are mentioned in the rules as possibility. The charge remaining at landing, that would be in volts. Decollage measurements, and what decollage is your wing incidence. So you can measure the height of the wing at the leading edge and trailing edge. The difference in those 2 measurements is your incidence. You can do the same on your tail. Measure the height at the leading edge and trailing edge. Now, this plane is not adjustable. Those 2 measurements together determine decollage. Decollage is the difference in incidence between your wing and your stabilizer. So you can use the wing and stabilizer measurements, if they're adjustable, as columns in your log sheet. The center of gravity is simply where the plane balances after it's ready to fly. And typically, there it's balanced on my finger, but we don't have the rubber on here, and this is quite a bit forward of the middle of the rubber motor. So you really need the center of gravity with the rubber motor on the airplane. Then you can add any other columns that you see fit. And then there's a requirement for at least 3 minimum flights. Some of my thoughts on electric Wright stuff. The electric components, especially the supercapacitors, may be in short supply. I believe the kit manufacturers will probably have a supply of those in bulk. But if you're ordering from, say, DigiKey, Newark, Mauser, Arrow, Amazon, those capacitors could get into short supply. So order early. Motors are not all created equal. You're probably going to use something in the 6 millimeter to 8 millimeter diameter case on the motor, but be sure to check the kV rating. kV is thousands of RPM, that's the K, per volt, that's the V. Or they might be rated in what the RPM is at 3 volts. Now, these motors, some of them are used in the quadcopter drones, and you will find that those drone motors tend to turn anywhere from 40,000 to 60,000 RPM on 3 volts. They might have a kV rating of 15,000 or 15 to 20 kV. That's 15,000 to 20,000 RPM per volt. That's way too high. We don't need thrust that's going to levitate this plane like you do with the drone. There's pager motors that look physically the same, 6 to 8 millimeter case and 14 to 20 millimeter length. And they're rated at 10 to 12,000 RPM at 3 volts. What does this allow you to do? You can use a considerably larger propeller at the same voltage to get the same performance. And with 40,000 RPM, you're going to need such a tiny prop, you're not going to get a much effective thrust. So be sure that you understand that there's differences in the RPM rating of the motors, and make sure you get something with a lower RPM rating, not something that's pushing 20 kV. There's a lot of props available. These props might be for drones, as you'd find on Amazon, or for airplanes that you can find through hobby suppliers. Probably for this class, if you find a motor that's in the 10 to 12,000 RPM, you're going to want something between 35 and 60 millimeters diameter on the prop. The other thing you'll want to do is check the prop shaft hole size against the motor shaft. Some of these motors have a 0.8 millimeter diameter shaft. Some of them are 1 millimeter diameter. The props may have either of those sizes or another size hole. These are a press fit onto the front of the motor. You want to make sure it's not a loose fit, it'll just spin. We have used some 1 millimeter props on a 0.8 millimeter shaft by putting a little thick CA in the hole, blowing it out to make sure you've still got a hole, and then pressing the prop on, and that's worked for us. So that's most of my thoughts right now on electric Wright stuff. It's a new category, and you're going to have to be willing to experiment. But some of the kits will come with the capacitor and a motor and a prop that make a good starting point. Don't be afraid to try things, or even try twisting the blades and see what that does to add more pitch or take away pitch to fly your plane. If you're getting into the rafters and have too much climb, it's the opposite of Wright stuff. You want to go to a smaller prop or less pitch to reduce your climb. Whereas on Wright stuff, you increase your pitch or go to a larger prop to decrease your climb. So keep that in mind. Okay, let's move on to Wright stuff in the C division. This is your rubber band powered duration plane. And some of the specific features on Wright stuff. First off, the prop is limited to a maximum of 24 centimeters. This is just under 9.5 inches. Be sure to carefully measure this, and I would make a 24 centimeter hole in a piece of paper or cardboard and pass your prop through it. It's not just the straight dimension. You can't take a 25 centimeter prop and straight clip the two ends off and expect to pass, because now diagonally from this corner to this corner is still over 24 centimeters. It's a diameter measurement. You need to fit it through a 24 centimeter diameter hole. The propeller can be built or it can be purchased as a whole. The plane must weigh at least 8 grams without rubber. That should be easily reached using any of the kits or using hobby shop wood and veggie bag for covering. It's not a difficult weight to reach if you control your glue. This gives you a 9.5 gram flying weight because the rubber motor is limited to 1.5 grams maximum mass. That includes any O-rings that you put on it. It can be weighed before or after lubing. Lube adds weight, so it takes away rubber. So I suggest you dry off your rubber as best you can with paper towels before checking it in, and then have a lube bag ready for when you're prepping your rubber motor for flight. The rules this year will allow up to 6 rubber motors to be processed. That's a new limitation to keep the processing time reasonable. Six rubber motors should give you a variety of lengths, so you can adjust your second flight based on what you observe on the first flight. In your log, the required entries are the motor size. That can be length, it can be width, it can be mass. It just says motor size, so you'll have to interpret what they're asking for there. We actually have the length, and then the width we typically measure in grams per inch. That's kind of a bastardized unit. We'll have to change that to grams per centimeter. But since the motor is limited to 1.5 grams, and if you're cutting them right to 1.5 grams, then the length of the loop before you ever wind it is going to be your best indication of motor size. The number of turns or the torque at launch. So if you wind up fully and then back off to reduce your climb, it's the at launch numbers that are required. And then, of course, the flight duration. Other additional columns, you have to have at least 3 more columns. The altitude, the torque, if you have a torque meter, the remaining turns or torque at the end of the flight, number of unwinds. So how much did you take out of the rubber from your peak wind to your launch wind in order to reduce the torque to a suitable launch torque? Propeller details such as pitch and diameter. And then anything else you can think of. One that we use a lot is our altitude on our first lap. That tells a lot about the launch torque and the matching of the rubber to the propeller. We said before, the log is critical to improving. Let's look at sources briefly. Where do you get this stuff? And we'll start with the kits. Ward Science is the official Science Olympiad supplier. Their kit includes some tools, some glues, everything you need to get started, knives. It's generally a more open-ended kit than some of the other kits, so there's less direct design and guidance. It's not as refined as some of the other kits, but it gives you everything. I believe it gives you a winder, so it gives everything in one place. They have not produced an electric Wright stuff in the past, but neither has anybody else. So you still may need to experiment with different motors, different propellers, and that kind of thing. Freedom Flight Models has been one of the most popular and most competitive planes over the years. It's consistently in the top 10 at nationals and has very consistent quality and extensive instructions. A lot of kids give up after they build it and forget that the instructions have many pages walking you through trimming the plane. Those are just as important as the build instructions. The Freedom Flight Models website also includes a full stock of accessories, torque meter, winder, counter for the winder, different sizes of rubber, different propellers, and so forth. So it's a pretty good one-stop shop to get you flying for Wright stuff, and he should have a good electric Wright stuff kit as well this year. J&H Aerospace um, is a fairly newcomer to the Science Olympiad realm, but Josh is a very accomplished indoor competitive flyer, and he has had some very good test flights on the planes for this year. His planes build up perhaps similar to the Freedom Flight Models planes. They're good, robust, well-designed planes. And he also has a lot of good YouTube videos, and he has a construction video as well as flight trimming videos. So an excellent resource. I can't say enough good about what Josh has done for the indoor flying supply chain. Laser Cut Planes out of Colorado is an excellent company. These planes tend to be a little simpler building. This P-18 that I was showing is typical of the construction of laser cut planes. He has a laser cut spar on the leading edge and trailing edge, and the ribs go into slots that are laser cut into those spars. So it's self-jigging, goes together really quick. You can build this plane, which would be very similar to his Wright stuff planes, in a couple of hours. We have a 3-hour video online building this exact airplane, and his Science Olympiad planes are very similar. So you want the simplest building, lowest cost, best all around for entry level. This is a great kit. In the past, he has had some modified plastic props when we had the really tiny props, but I believe he's doing a built-up prop now. So he may be doing the Ikera. I'm not sure, but simple assembly, good flying planes. You can't go wrong with laser cut planes. Guru Engineering is also a fairly recent addition. They're a nonprofit, so their costs sometimes are a little better than some of the other companies. He got his start by supporting a team out of West Virginia, and they won at nationals about 5 years ago, and that's where he got his start, and started putting together kits and selling them nationally to help out students across the country. So I think the construction is going to be similar to laser cut planes. It's going to be all balsa instead of a balsa and carbon setup. Some of your accessories: rubber props, winders, torque meters, covering. Indoor Free Flight Supply is a good company to get a lot of that from. It's actually run by Dave Lindley, president of NIFAS. Freedom Flight Models has a lot of good basic tools and rubber for Science Olympiad as well as TSA. FAI Model Supply is where you're going to buy bulk rubber. If you want to strip your own rubber and buy it by the pound, that's the place to get it. And they also have a good stock of Ikera props. And then J&H Aerospace is continually improving his selection of torque meters, winders, and other support equipment. Indoor Model Specialties, that's where you can get your best low-cost, quote-unquote, rubber stripper. The rubber stripper is going to cost you about $200 delivered. He'll sell you prop hangers, prop bearings basically, and covering. He may not yet be delivering due to the COVID pause. So you may not get a hold of indoor specialties till later in the season. Plans, you can look on Hip Pocket Aeronautics. It's another forum, and they have a plans gallery, and look for plans by Bill Gowan or Brian Turnbull, and you've got plans going back a number of years from both of those. Other online resources, NIFIS or the Free Flight Society has a page just for Science Olympiad. This page has sections for students and coaches and so forth. It includes videos. We have a YouTube channel that'll link to, and we have playlists on that YouTube channel specifically for Science Olympiad. And all you have to do is ask, and we'll make more videos. We're constantly adding new videos. There's plans there. We do have a link for Bill Gowan's 2022 Wright Stuff plane. The Scioli forums are an important resource. This is where you can go and ask questions, and you'll get pretty quick responses from several of the coaches from NIFIS. The Hip Pocket also has a forum, and specific for Science Olympiad. It's more aimed at coaches than students, but I've received good help from there in the past, and I'm usually on that side as well. There's a couple of links in the slides here for minimizing weight gain. That's looking at how you put glue on. We also have a video on our NIFIS YouTube channel on minimizing weight gain with glue. There's some basic building resources, PDFs, also on the Science Olympiad site. And we have the build video for the P-18 airplane, which is going to be very similar to the Wright Stuff and electric Wright Stuff planes. That video is on our YouTube channel. So in my opinion, the most important resource to have there, the growing resource, is the freeflight.org Science Olympiad site under their Join, Learn, Fly section. That's going to be an expanding area of resources, and it has links to all these other resources. So check us out there. Let's look briefly at building techniques. Weight control is everything. For Science Olympiad, using thin cyanoacrylate should work well. Thick or medium cyanoacrylate is going to add a lot of weight. You want to have good glue joints to start with, so a minimal amount of glue will bond the balsa together. And what's shown here is a capillary applicator. It's basically two pins in a piece of balsa wood, and they come to almost touch each other. You squirt a little bit of thin CA on a piece of aluminum foil, a piece of wax paper, or I like to use a lid from a margarine container, and just dip that tip in there, and it gives you the tiniest drop, and you just touch it to where you need glue, and it'll wick itself into the balsa. Balsa density is important for weight. If you're buying your own balsa, you want to weigh it and grade it. You want to bring a scale to the store and weigh every sheet. You want balsa in the 5 to 8 pound per cubic foot range. For Wright Stuff, 8 pounds per cubic foot is fine. But if you go to Hobby Lobby, you may find wood that's 16 to 20 pounds per cubic foot. And that's going to be way too heavy. All of the kit makers that I mentioned do a really good job of grading their wood, and so you can't go wrong with what comes in the kit. But if you're building your own, you need to calculate the volume in cubic feet of a sheet of wood, and it's going to be well less than a cubic foot. And then measure it in grams and convert that to pounds, and figure out what weight a sheet would give you something in the 5 to 8 pounds, or just use 8 pounds as a maximum, and weigh every sheet. You need to build straight. Use fixtures. Foam board allows pinning. You can use glass or a piece of melamine covered wood from the hardware store, but I really like using the foam boards because you can pin things down. Sometimes getting strength in a joint is difficult. The balsa to carbon joints sometimes are not fitted that well, or especially a carbon to carbon joint. And so sometimes we'll wrap a carbon to carbon joint with a little bit of thread, like 1 or 2 wraps of sewing thread and just a dot of thin CA. Carbon is very light and very stiff, and it's being used by several of the kit makers. It is more expensive, and it takes a little more to get a good glue joint. One of the keys for good glue joints is the fit has to be perfect before you ever put glue on the joint. A fit with gaps is going to take a lot of glue. It's going to make a brittle joint. So, covering. This is another area that a lot of people ask questions. Most of the kits use a covering called Ultrafilm. This is a little bit thinner than the grocery veggie bags, and I'm not talking about the grocery bags you get at the front of the store. Go back to the vegetable section, the really thin bags. Those make a great covering material for the 8-gram range planes, but Ultrafilm is used in most of the kits. In order to cover with Ultrafilm, we make a frame that will support the Ultrafilm, and we just make that out of scrap wood, and then we build our structure on our board pinned down, and then we take a piece of the covering. It cuts very well with soldering iron. If you're using the veggie bags, you can cut it with scissors, but with the Ultrafilm, if you cut it with scissors, you're going to tend to tear it. So a soldering iron is the best thing that you might have laying around the home to cut that film. You can cut it with a sharp razor, but if you end up with a little nick in it, it's going to tear from that nick. Ball it up as small as you can, as tight as you can, unwrap it, and then do that again. And as you unwrap it, you're pulling out from the middle, combing it with your fingers. I like to use Vaseline or lip balm on the balsa wood frame, this frame that's supporting the covering, and then carefully stretch the covering onto that frame. You don't want it real tight. You want it to sag a little bit. For adhesive, we use 3M77. This is a spray adhesive. You can get it from Walmart. And you could use a glue stick, but I've seen too many ribs get broken by using a glue stick. 3M77, when you spray it, gets on everything. So take it outside, spray it, put some newspaper down on the sidewalk, spray it outside. Use as light a coating on the top of your structure as possible. The top is the convex side of the ribs, and just right over top of it, let that settle down onto it, and that's all you need. Then take it to your frame where you've stretched your covering and turn it over and press it down into the covering, and it'll stick right away. Allow it to cure, and then your best bet for cutting it out is a soldering iron. You can get a medical cautery from Amazon or from Indoor Free Flight Supply. That works great because it's battery powered, so you don't have a cord whipping around, but a soldering iron works well. Just be careful if you have carbon leading edges and trailing edges that you don't dwell very long with the iron touching the carbon. It will melt the glue that holds the carbon together, and then you'll ruin your carbon. So you got to move fast enough, but not too fast. If you move too fast, you'll tear it. You might want to try some practice runs on an area away from the pieces you're covering, just to see how fast you should move the iron. And if you have a pretty hot iron, you want to keep it away from the carbon, and the covering will melt back from the heat of the iron closer to the covering. Let's look at flying. So while you're trimming your plane and flying it, verify your mass often. As glue is added to repair, you're going to remove ballast. You want to verify your center of gravity often. If you repair something on the tail, it's going to get tail heavy and you might have to add a little clay to the front. So those two measurements you want to verify often. Decollage. Typically, we're setting the tail at 0, 0. In this case, it's glued on, it's not adjustable. And then a good starting point is 5 to 10 millimeters at the leading edge, difference between the leading edge and trailing edge. So the leading edge of the wing is higher than the trailing edge relative to the motor stick by 5 to 10 millimeters. Now on this year's plane, we just did some flying on it and we found 3 to 6 millimeters is probably your better range. But I would set it for 3 to 6 millimeters difference between the front of the wing and the back of the wing. And then wind a light load, 600 turns, 500 turns on the motor. And then you're going to launch it straight ahead with just a light toss. And what you're looking for is in the slow flight, because you haven't wound it up tight, if it's stalling a little bit. So it goes up and it drops, goes up and it drops. Then you want to decrease the wing incidence or move your CG forward just slightly, small adjustments. If it's not stalling, then you're going to increase your wing incidence or move your weight back, move your CG back until you do start getting a little bit of stall. So that stall is something that you want to look for toward the end of the flight. And once you get a little bit of stall, then lower the front of the wing maybe a millimeter or move the CG forward 3 to 5 millimeters until that stall goes away. Then you're pretty close to the optimum incidence and center of gravity combination that'll fly. Now, if you have to have 10 to 15 millimeters of wing incidence to induce a stall, you've probably got your CG too far forward, and that's going to be a lot of drag because the weight is trying to pull the nose down, so the wing is working hard to pull the nose up and getting a lot of lift to correct for that improper center of gravity creates a lot of drag. So your trimming is a balance between your center of gravity and the amount of incidence in your wing. Now, if you get your center of gravity so far back that it's flying well with very close to 0 incidence in the wing, that's fine. It's a very efficient setup. But if you hit a girder, which you will, it's not going to recover well. And the plane will dive down 10, 15 feet before it recovers. It may dive all the way to the floor. That tells you you've got a less than optimum stability on the plane, and you want to move your CG forward and readjust your incidence for a little more incidence, and that'll give you more stability. So watching for recovery from ceiling touches will tell you what to do on your trim. Some of the other basic parts of the trim here, because of the way the propeller is turning, the plane is going to tend to want to turn left, but we want to help it out doing that. So what we've got on this plane is a little bit of left bend in where the tail boom mates to the motor stick. We did that when we were gluing it together. If you don't do that, you can wet this part and bend it some and then hit it with a hairdryer or a heat gun while holding that bend in to get 3 to 5 degrees of left turn on the rudder. The second area is if you look from the trailing edge, the stabilizer is tilted to the right of the plane. So the left edge of the stabilizer is higher than the right edge. And the reason for this is the stabilizer has an airfoil. It is lifting, but it's lifting slightly to that side. That's going to pull the tail to the right, which turns the plane to the left. Your rudder offset will tend to affect the circle of the plane at higher power flight. The tail tilt will tend to affect the circle of the plane toward the end of the flight at low power. So those two work together. You may also want to experiment with a little bit of left thrust. If you're having trouble at the very highest power right at launch, you could add a little bit of left thrust. Not all of the prop hanger assemblies are easy to add left thrust into, though. One other area, doesn't look like there's much in this one, would be wash-in. If the plane tends to, at high power, roll up too much and start spiraling in toward the deck, but at medium and low power, it flies great. What you want to do is add some wash-in, and that is taking this leading edge on the left wing and raising it up higher. You can do that by bending the wing post to the right to raise that left wing leading edge and raise the right wing trailing edge. It only takes a few millimeters of wash-in to correct that. Any more than a few millimeters and it's too much drag. I would start with 0 wash-in to begin with, and then add it only if you need it at the most high-powered launches. Trimming may take 1 or more flying sessions, and it's something that's ongoing with your airplane, especially as you repair and modify your plane. Each launch after you got basic trim can go higher power, and you're adjusting the launch torque to the room height. You don't want to be banging too much against the girder, too much risk of hanging it up. You only get 2 flights. You do want to wind to the full torque capability of the rubber. So right up to almost braking, and that's your highest torque, and then back down on the winds until you're at the torque the launch torque that you want for the room height. This will get you the most number of winds in the rubber and get you down to the torque that you intend to launch at. Record all of your parameters in the log, but only change one thing at a time. If you change 2, 3, 4 variables at a time, you don't know what improved the flight or what hurt the flight. So change one thing, fly it. Change another thing, fly it. There's a lot of interactions here, and the more data you get, the better. Optimizing the rubber to the propeller is the key. You'll want to change props. We typically have 20 to 30 props in Wright stuff during a year. You can adjust the prop pitch on these Icara props. You can grab the spar of the prop with 2 pairs of needle nose and just twist that spar a little, but you'll want a pitch gauge to make sure you have the same pitch on both blades. The rubber width and therefore length of the loop has to be changed. So if you go to more pitch, you're putting more load on the prop, you're going to need a thicker piece of rubber, which will make a shorter loop. The stopwatch tells you everything. So believe your stopwatch. If something went in the wrong direction, then go back the other direction and improve your time. If it won't climb, either try thicker rubber or less pitch or less diameter on the prop, but I don't recommend going down below the maximum diameter. One trick that we've used is half rubber flights. On a half rubber flight, you use a 3/4 gram piece of rubber instead of 1.5 gram. It's half the length, but it's the same thickness or width as your rubber you're going to use. You replace the other half with a stick. It's got some hooks, could be staples or pieces of music wire, and you make that stick weigh exactly 3/4 gram by adding clay and make sure it's balanced in the middle of the stick. This half rubber will climb half as much as the full rubber, and your time will be almost exactly half what you would get with full rubber. So this is great for testing in, say, a 25-foot gym when you know your contest is going to be in a 40-foot gym. So you try and get a 20-foot rise on the flight, and then you know when you get to full rubber, you'll have a 40-foot rise to the flight. Bottom line, get in the gym. Winning takes a lot of flights. On Wright stuff, let's talk Wright stuff specifically. This top chart shows the hysteresis in rubber winding. The top line, the dotted line, shows the torque as you add more winds, as you wind it. And then the solid line shows the unwind. And you can see there's less torque as you unwind. That's called hysteresis. And that's why we want to wind it up till it's approaching breakage and then unwind to your launch torque, rather than just winding up to a specific torque, because you'll immediately drop down a lower curve and not have as much power as you thought you would. And you're not going to get as much winds into the rubber. Wind off the airplane. Rubber does break. And if your rubber motor breaks while you're winding it, you don't want your airplane being twanged by the rubber band. Use a torque meter if at all possible. There's some low-cost torque meters by several of the suppliers, and this is the only way to get accurate launch torque to control your altitude in the gym. Count your winds. I highly recommend a digital counter on your winder. I know Freedom Flight Models has that option. Lubricate your motor with silicone oil. You can get this at a hobby shop. It's used for shock oil for RC cars. Or you can use Armor All. This is available at any automotive store. It's used for leather seats and so forth. But it's basically a silicone oil suspended in water. You're going to wind almost to braking, so you need to know what torque it's going to break at. So you need to break some rubber to know how high not to wind it, and you wind it just short of that breaking point. And then you back off to your launch torque. You can see in the lower picture, the young lady is stretch winding. She's stretched the rubber 7 or 8 times the length of its relaxed state. And then she's putting in at least half of the winds at full stretch. And then she's watching the torque meter as she walks in. And you're also about half of your braking torque when you start walking in. And the torque will ramp up as you approach the stooge on the winding table. In looking at whether you have the right rubber for the prop, the initial climb is going to be fairly steep, and that is based on your launch torque. So you can adjust your launch torque to affect your initial climb and in effect change your maximum altitude. The cruise, once the plane starts leveling out, it's barely climbing for a while and then it's barely coming down. That's based on the rubber and prop balance. So if it's not cruising well, if it's coming down too quickly, you might need slightly thicker rubber. If it's running out of rubber before it lands, you might need slightly thinner rubber. Letdown, that's the final few orbits of the plane as it comes down to the floor. You can improve the letdown by using what's called a flaring propeller, and that has a blade that will flex based on how hard the motor is trying to turn it. There's an Ikera prop that is a flaring prop, and that's a good starting point. Look at the turns remaining, right? I record that, and our team records that in the log. Ideally, we've seen on Science Olympiad about a half a row of knots on the wound rubber is about right on landing, but your mileage may vary. Electric Wright stuff. Again, record all the parameters and change one thing at a time. Start with low power. You can charge to a lower voltage or do a runoff of the charge before launching. So maybe turn the motor on and run it for 5 seconds. Then next flight, run it for 3 seconds before launching. That reduces the power in the capacitor. So you don't, first time you launch it, end up in the girders. So increase the voltage at launch to gain more altitude or decrease the amount of runoff. Adjustments. These props tend to be a flexible plastic to begin with. I've had some luck with twisting just manually into the prop, but that tends to relax back out. So if you're going to change the pitch of the prop, you're probably going to have to add some heat with a heat gun. You need a pitch gauge to do this accurately, and the pitch gauges out there are not set up for these little props. So you may have to make your own pitch gauge. More pitch means more climb and a shorter duration because it's using more power. But if your plane's not climbing enough, you can either go up in diameter or up in pitch to get more climb out of it. But then you're taking more power the entire flight, so it may reduce. You have to look at your stopwatch. Don't be afraid to cut a prop. You have plenty of props, they're cheap. Experiment with different diameters. Just cut evenly, make sure it's balanced. CG and decollage, generally, we found you want to get the plane trimmed for your letdown, for the end of flight. You want that not stalling. You may find adding a little bit of incidence on the wing may help climb a little steeper. But at the same time, if that adds a lot of stalling at the end of the flight, it's not a good idea. So on the electric Wright stuff, I think for altitude control, you're going to look at more prop pitch and prop diameter than you will CG and decollage. But keep in mind your CG and decollage combination may impact the way the plane climbs as well. So flight adjustments, if your initial flights are pretty good, make small changes and record the differences and record your flight time. If it dives or doesn't climb, or your late flight is too flat or even coming down too steeply, try increasing decollage, raising the front of the wing or raising the back of the tail stabilizer, or move the CG to the back if you already have enough decollage. As we mentioned earlier, you want to move that CG back or raise the front of the wing, raise the decollage until it starts to slightly stall, and then back off from there a little bit. Stalling is the opposite of diving, so nose climbs and then dips, climbs and dips. You want to do the opposite, decrease the decollage or move the CG forward. If it only stalls at high power, so at a high power launch, you point it up some and it goes up sharply into a power stall and it stalls, you might have to add some down thrust, get your propeller to point down slightly. If your prop hanger doesn't allow that, you could add some incidence to the wing and add some incidence to the tail. You haven't changed the relative decollage between the tail and the wing, but you've essentially pointed the motor stick down a little, effectively giving you a little bit of down thrust. So that's one way to add a little bit of down thrust. If the flight is okay, but the climb is limited, on electric Wright stuff, try increasing the pitch of your prop a little bit or increasing the diameter. On Wright stuff, you want to decrease the pitch to get a little more power early in the flight. Small adjustments, 3 to 5 degrees on Wright stuff will make a big difference. If, as I mentioned earlier, if it's tending to roll in and won't climb, you can add some wash in to the left wing, and that will help you climb in the initial high power part of the flight. Again, if your decollage isn't right, if your end of flight is not on the verge of stalling but not quite stalling, then it may impact your climb. But you don't want to change your decollage and CG setup just for your climb. It's more important to have that correct for your cruise and let down. And control the climb with your prop and and power plant. So that should be enough to get you started on flight adjustments and some things to look for as you explore the flying characteristics. We have my contact information for follow-up, but I prefer you use the Scioli forum to contact me if you have questions. That way, I'm not answering the same question many different times for many different people. This follow-up slide may also be modified by different people using this presentation, and they can put their own contact information in here. I want to thank you for your attention, and I hope that this short presentation will help you get started with your students in successfully flying this year's Wright Stuff and electric Wright Stuff planes. Thank you for your time.